As physicist Riess once said, the mismatch between the universe's observed expansion rate and the predictions of the Standard Model suggests that our understanding of the cosmos is far from complete. And when even a Nobel Prize-winning scientist admits that we've reached the limits of our cosmological knowledge, you know the situation is serious. The James Webb Space Telescope has once again confirmed that the universe doesn't behave the way our theories say it should. In reality, it's expanding significantly faster than our models predict. Today, we'll dive into what's known as the Hubble tension, why it's such a challenge for our overall picture of the cosmos, and what possible solutions scientists are exploring, including why Albert Einstein himself may have been fundamentally wrong about a key idea. But first, let's tackle a simple yet essential question: how do we even know the universe is expanding? To answer that, we need to rewind about a century, back to a time of groundbreaking discoveries. Back then, many of the world's leading physicists, including Einstein, still believed the universe was neither growing nor shrinking. Instead, they saw it as a completely static structure, fixed and unchanging for all eternity. Even at that time, there were daring voices that challenged the prevailing view. Among them was the Belgian priest and astrophysicist Georges Lemaître, who demonstrated that Einstein's general theory of relativity could be used to construct a mathematical model of an expanding universe. His approach had a decisive strength: it led to a prediction that could be tested through observation. If the universe was indeed expanding, then other galaxies must be moving away from us. Much like dots painted on the surface of an inflating balloon drift apart, the same would happen with galaxies. In this process, the light they emit would be stretched during its journey to Earth, lengthening its wavelength and shifting it toward the red part of the spectrum, a phenomenon known as redshift. In the years that followed, astronomer Edwin Hubble confirmed exactly this. Through meticulous observations at the Mount Wilson Observatory in California, he found that light from countless galaxies was indeed shifted toward the red end of the spectrum, providing direct evidence for the universe's expansion. It's important to note that the cosmos is not expanding into an already existing space, rather, space itself is growing. And as if this revelation wasn't profound enough, it led to an equally revolutionary implication: if the universe has been expanding continuously, then logically, in the distant past, it must have begun from a single, incredibly small starting point, from which everything we know once emerged. Today, we refer to that tiny initial point as the original singularity. Even in the early days, scientists like Lemaître and Hubble were already making groundbreaking contributions to what would become known as the Big Bang Theory. In the 1990s, however, astronomers uncovered a surprising twist: the universe wasn't just expanding, its expansion was actually speeding up. This unexpected discovery demanded an explanation. To account for this acceleration, researchers proposed the existence of dark energy, a mysterious force that appears to oppose gravity and still eludes full understanding today. This leads us to the Hubble tension, a fundamental question: exactly how fast is the universe expanding? While it might sound simple, this question lies at the heart of a long-standing cosmic puzzle. Let's start with the basics. Galaxies drift away from each other at a speed proportional to the distance between them. Put simply, if Galaxy A is twice as far from Earth as Galaxy B, it will also recede twice as quickly. To calculate how fast two galaxies are separating, you need to know their distance, and then multiply it by a constant. That constant is the Hubble constant. And here's where the mystery deepens. The results we obtain depend directly on the method of measurement. One such method relies on cosmic microwave background radiation, an almost perfectly uniform relic from the early universe, essentially a baby photo of the cosmos. By combining this radiation data with theoretical models of cosmic evolution, researchers can estimate the current rate at which the universe is expanding. Using this approach, scientists arrive at a Hubble constant of about 67 kilometers per second per megaparsec. To put that into perspective, 1 megaparsec is roughly 3.26 million light-years. 1 light-year equals about 9.46 trillion kilometers. In simpler terms, this means that for every 3.26 million light-years of distance between two galaxies, they move away from each other 67 kilometers per second faster, which is about 244,000 kilometers per hour per megaparsec. However, things get even more intriguing. As mentioned earlier, the value of the Hubble constant changes depending on the measurement method. When scientists use direct astronomical observations, such as those involving supernovae, gravitational lensing, variable stars, or red giants, they calculate a faster expansion rate, 73 kilometers per second per megaparsec, about 264,000 kilometers per hour per megaparsec. This is a difference of around 20,000 kilometers per hour per megaparsec from the theoretically predicted value. This mismatch is known as the Hubble tension. So, how can it be explained? The simplest possibility is that it isn't a real phenomenon at all, but rather the result of earlier measurement errors. To put this theory to the test, a team led by Nobel Prize winner Adam Riess used the James Webb Space Telescope, and their findings were sobering. Webb's observations only deepened the mystery. In an effort to revisit the so-called Hubble tension, researchers at Johns Hopkins University examined several cosmic distance markers, supernovae, variable stars, red giants, and a rare class of carbon-rich giant stars, which Webb had been studying for over 2 years. They then compared Webb's distance measurements to those from the Hubble Space Telescope. The result? The discrepancy in the Hubble constant persisted even in Webb's most comprehensive dataset to date. Across all measurements, the Hubble constant ranged between 72.1 and 73.4 kilometers per second per megaparsec, with a combined average of 72.6. This strongly suggests that simple measurement errors are no longer a convincing explanation for the mismatch. As Adam Riess summarized, the discrepancy between the observed expansion rate of the universe and the predictions of the Standard Model suggests that our understanding of the universe may be incomplete. With two NASA flagship telescopes confirming each other's results, we must take the problem of discrepancies in the Hubble constant very seriously. The so-called Hubble tension might be a sign that we've overlooked something fundamental about the universe. It's possible that the faster expansion of the cosmos is driven by a process or force not yet accounted for in the Standard Model of cosmology. According to Riess, this could involve an exotic form of dark energy or dark matter, an entirely new particle or field, or even a flaw in our current understanding of gravity. In fact, one potential solution could lie in adopting an alternative theory of gravity, something that would require setting aside some of Einstein's long-standing assumptions. Could Einstein have been wrong? A simpler explanation suggests that the Milky Way may be located inside a supervoid, a vast, empty region of space. Research teams from the universities of Bonn and St. Andrews argue that this alone could explain why we observe a faster cosmic expansion. Large-scale surveys reveal that the universe's largest structures aren't scattered randomly, but are arranged in a massive cosmic web. This network consists of filaments, dense, thread-like regions of matter, that, together with vast voids, create enormous, nearly empty bubbles. To illustrate, the researchers compare our Milky Way's position to an air bubble in a cake. The surrounding matter is denser, creating gravitational forces that pull galaxies inside the bubble toward its edges. This arrangement could help unravel one of modern science's most puzzling mysteries. When applied to the Hubble tension, this idea suggests that galaxies are moving away from us much faster than expected because they're influenced by a local underdensity. At first glance, it makes sense. However, there's a significant problem with this hypothesis. The Standard Model of cosmology doesn't account for such large underdensities or voids. According to it, matter in space should be evenly spread out. But what if the Standard Model doesn't truly reflect the universe's reality? The researchers behind the study considered the same question. They noted that our current model is rooted in Einstein's theory of gravity, and even the father of relativity might not have been entirely correct. Perhaps gravitational forces behave in ways Einstein never predicted. To explore this possibility, the scientists turned to a different approach, a modified theory of gravity, specifically modified Newtonian dynamics, MOND, introduced in the 1980s by Mordechai Milgrom. Mond explains the rotational behavior of galaxies by altering the equations of motion for matter in a gravitational field, completely eliminating the need for mysterious dark energy. Interestingly, this alternative theory also predicts the existence of massive cosmic voids, a key factor in addressing the Hubble tension.